Hi, my name is Anthony Colaprete. I'm the project scientist for the Resource Prospector Mission. Thank you for letting me give you a brief talk on it today. The Resource Prospector Mission is motivated by really the revolution in our understanding of water on the moon, and really preaching to the choir here in this group about how important and exciting this revolution in our understanding has been over the last decade or so. This chart just kind of reminds us that there's a wide range of possible distributions and concentrations of water that we've discovered, everything from the fractions of a percent across the entire lunar sphere to more enhanced areas or increased concentrations in the several percent range, like we see in some of the permanent shadowed craters like Cabeus, or even greater concentrations in the 10 to 100%, meaning nearly pure chunks of water ice, according to potential radar signatures. So there's a lot we've learned over the last 10 years about its many forms and distributions and concentrations. But what we're missing is a lot of the understanding at the scales most important for resource utilization. One of the other things we've learned is that it's most likely heterogeneous, meaning it's not uniformly mixed, it's not evenly filled from one crater, cold crater, to the next cold crater. And so there is some processes at work, sources and sinks, that lead to a distribution that is not yet fully understood. If we just look at the L-cross data and the neutron data from Lunar Prospector or LENS, we understand that the water is most likely patchy at the 20 to 40% level, meaning that it's mixed, it's heterogeneous at scales of probably tens to hundreds of meters. We understand this from actually some modeling, for example, like in Hurley and others have done on impact cratering and the gardening that it does. And so we really at least have some sense that the mixing at least some of the scales, hundreds to tens of meters, is important to understand. And it's very difficult to understand this, obviously, from an orbital measurement, especially when we start concerning ourselves with vertical mixing. The cartoon on the right is one interpretation of an L-cross result, that we do think there is a distribution with depth of varying concentrations. Theoretically, there's reasons for this as well. So we really need to understand this kind of mixing, both laterally and vertically, at the level at which we would access it for resources, meaning I call it the human level. How would you identify and locate these kinds of resources? This slide takes that to a step further, that concept a step further. We really ultimately need to determine the operationally useful deposits of water ice on the moon if it's to be used as a resource. And so to that end, we really need to assess the extent of the resource or body. And again, these cartoons kind of restate what I just did on the previous slide. We need to understand the lateral distribution across scales of hundreds to tens to hundreds of meters, kilometers. We need to understand how is it mixed vertically. Is the top layer always desiccated? Are there frosts right at the surface and PSRs, et cetera? And then we need to understand its distribution with depth and its concentration as a function of depth and lateral distance. Are there lenses, or is it patchy? Are there layers, et cetera? And if we get this kind of information, that really helps us understand how operationally useful it is. How much area do we need to excavate to acquire a certain amount of water? What's the energy, the effort needed to actually excavate this material? So all this actually is really pretty important to get some first order estimates on how useful the ore body is, water on the moon is, for human exploration. So that's this has been a long-standing question. This shows some concepts that the League group put together many years ago, or 5 years ago, it's many now, where they're really looking at the next steps in understanding the lunar surface and lunar resources. One of the first phases that was mentioned was this prospecting, this lunar resource prospecting. I won't read through these bullets, But this was really the initial concept for a payload called Resolve, and then ultimately a mission called Resource Prospector, to actually try to address these points in terms of identifying where the resources are, characterize the environment in which they're found, so you can extrapolate to other environments, and understand exactly how can we get at them, how available and viable are they as a resource. And that's what Resource Prospector is really all about. As you know in this audience, there were a number of efforts spanning years to develop what the strategic knowledge gaps, SKGs, were for exploration to the moon, Mars, the moons of Mars, etc., asteroids as well. Here I show how the Resource Prospector Mission aligns to a number of lunar SKGs. It shows about 22 of these. On the left is the strategic knowledge gap. The next two columns is the instrument activity that Resource Prospector brings to the question. And then this final column shows the relevance that Resource Prospector has to it. So green being very relevant, yellow being less. We definitely, the Resource Prospector Mission definitely addresses a number of these key strategic knowledge gaps. So what is the Resource Prospector Mission? It really is a prospecting mission, but it's also a ISRU demonstration mission. So it's a two-in-one. The first part, the prospecting, is really meant to characterize the distribution of water at the poles, other volatiles as well. It's really meant to address that question of heterogeneity. Where is it laterally and vertically at scales of tens to hundreds of meters up to kilometers? We'll obviously design very much to look for water and measure water, but we can identify a number of other species. Important volatiles have been identified at the poles of the moon, and also go beyond and at least measure some isotopes, or have the capability to measure some isotopes, so we can actually learn potentially about the sources and sinks of some of these volatiles as well. We also want to demonstrate ISRU. Now, that's a pretty broad term, but for Resource Prospector, what it really means is being able to excavate material, locate, excavate material, handle it, put it into equipment to be processed, and then sampled and demonstrate that you can actually go from a ore to a end product, water. And we're going to do that with any volatiles we found in the dirt, but also can potentially do oxygen reduction with hydrogen we bring with us, and very high temperature soil, heating the soils to a very high temperature. So really, through this mission, we're going to demonstrate a lot of the hardware, the handling, and the process of going from ore to product on the moon for the first time. These are some of the paraphrased level 2 requirements for the mission. It's been broken into both minimum and full success like most missions, but we also have stretch goals. I'm not going to get into these in any detail, but ultimately the principal goal is to measure, to prospect and make measurements at multiple locations, at a minimum separated by at least 100 meters, and for full success, of course, at least a kilometer. That's really important. We're measuring both the surface and subsurface down to a meter with a drill. And also, and this is the part that engineers hate and we love, we the scientists, is we will make measurements both in shadowed and illuminated regions, meaning the rover will have to go into permanently shadowed regions to make the measurements. The next few cartoons I put together in PowerPoint, so I apologize for their crudity, but it demonstrates the various segments or operational segments of the mission. Prospecting, which you've heard us talk about. I'm going to talk about the payload here in a second, but basically we use 2 prospecting instruments to map the potential concentration of water or hydrogen as we drive. When we find a region of enhanced hydrogen or water, or just an area of keen interest, we can make a decision real time to stop and auger and or sample, and the particular drill we have allows us to do both. We can drop down an auger and do some quick, what we call near surface or quick assay of material brought up to the surface, or we can actually take that material and process it in our oven and bake off any volatiles that are in it. And we continue to do this mapping as we go along, looking for volatiles and demonstrating basically how we can extract and utilize regolith on the surface to make water. This is the toolbox, if you will, the payload that we bring to the lunar surface. Of course, we have a rover shown here on the left. And for prospecting, we carry two instruments, a neutron spectrometer and a near-infrared spectrometer system. When we find a place of interest, we can drill. This drill allows us to auger down to any depth up to 1 meter, bring materials up for the near-infrared spectrometer system to analyze real-time, or if we choose so, we can take some of the samples and bring it over to our oven, our oxygen volatile extraction node, which is an oven. Basically allows us to heat it up to about 900 degrees centigrade and burn off volatiles. As we bake off those volatiles, we can measure them with a gas chromatograph mass spectrometer system called LAVA, the Lunar Advanced Volatile Analysis. So we have a very capable analytical lab that we bring to the moon. And this toolbox, if you will, allows us to really identify, locate, and analyze the materials that we're interested in. So where are we going with this? The landing site selection process is really dictated by our level 1 requirement here, and that's what I show, our very first level 1 requirement. For full success, we need to land in a polar location. We can't do this in the equatorial regions. We need to maximize the chance for obtaining high volatiles, hydrogen in particular, and also maximize mission duration and traverse capabilities. What that means is, what that translates to is a Venn diagram similar to this here, where you have traversable terrain, the potential for volatiles. Being able to talk direct to Earth, that was a key requirement that comes out of design trade, not necessarily a level 1 requirement. And sun illumination, again, that comes out of design trade. These two allow for an affordable mission, i.e. no relay comm satellites or nuclear power plants. So for site selection, we have to find the sweet spot within this Venn diagram, and thanks to LRO and other missions, the M-Cube data set, et cetera, we have a great data set that allows us to identify these areas, and we have, and there are quite a few. We've done a number of site selection practices just to show that the mission can close. This is one for an area that is northwest of Hayworth. Hayworth is down here. This area is a nice indention with a PSR here, some hydrogen associated with it. And we've demonstrated that all of our requirements for direct-to-earth comm, slopes, et cetera, all are met with this landing site area. And we do that by actually building traverses to it. This shows an example of traverse. The red areas are permanent shadowed areas. Scale bar here is about 1 kilometer. And each of these points here is some place where we've stopped and done drilling or processing. For example, here's where we go into a PSR area, grab a sample, come out and process it, go into another PSR. And we've done this several times in a number of ways. We're full of power, thermal, and data modeling to really show that the entire design closes and we can meet all of our requirements. So in summary, I've got one summary slide here, and then I'm going to tell you a little bit about what we're doing this year. Resource Prospector was really built out of the findings of LEAG and other efforts to address some key strategic knowledge gaps, lunar strategic knowledge gaps. It has a very robust payload that addresses a number of these from multiple angles, which is always good. We've been working on landing site selection for the last 2 years and really developed the tools and the methodologies and processes for identifying sites, and we're very optimistic that there are a great number that actually will suit our needs. And at one point I want to make here is we will be having a Resource Prospector Site Analysis Workshop this summer, and in the fall that will be co-timed with the Exploration Science Forum and LEAG. You should see an announcement on that very, very soon from Survey. And we've basically, as I said, have been able to plan out the mission and show that it closes. We had a mission concept review about 1 year ago, and we passed that very well. So in my last minute that I have here, I'd like to really just talk about what we're doing this fiscal year. So we're still in a phase A and developing some of our key requirements and working out some of our key partnerships for the lander in particular. So this year what we decided to do was really demonstrate the rover payload op system. And by that, what I mean is we are building basically a prototype of the rover, demonstrating operations and remote operations from NASA Ames. The rover will be built at Johnson and operated there. We'll do full-up drilling, processing, and operations all this year. And that's essentially what we've been working on since last October. Hardware's coming together now. The payload's in its final integration steps before being delivered to Johnson for integration onto the rover. These remote operating tests will occur in August of this year out of NASA Ames. Similarly, we're doing tests of individual components to get ready for flight, to develop these instruments. This is an example of the drill being tested in a thermal vacuum chamber at Glenn Research Center. Here we're able to chill down to minus 100 degrees centigrade, a 1 meter core sample with some kind of doping of water, and that's what this is shown over here. On the right here shows the depth and where we put a 5% layer of water. And what we had in here was the Nervous instruments with its viewing ports here with the drill all in vacuum at cryogenic temperatures, and we operated this to make measurements with the drill to see if we could see water like we planned to do it on the moon. This shows some of those results. This shows the wavelength range for Nervous and the normalized brightness. And each of these colored curves is one drill. Basically what we do is we drill down 10 centimeters at a time. We call it a peck. And we bring those cuttings up to look at them. And you can see D1, D2, D3, and D4. These are each of those depths where we go down into that deep wet, into that wetter soil. This shows the fundamental band and the first overtone band of water ice. Overplotted here is a laboratory spectrum. So we're able to see very small concentrations of water ice. Actually, this dip right here in the fundamental corresponds to about 0.25% water ice by weight in the soil. And then we can actually map out those band depths with depth. So basically this shows that we can actually reconstruct with this drill, this drilling technique in Nervous, this wet layer in the soil that we could see before. So this is ongoing as well. This year is basically maturation of the technologies, the instruments, and the methodologies for making the measurements that Resource Prospector will make. And with that, I thank you for your time and open up to any questions.